Hello everybody. So today I'm going to be going over the problems in yesterday's contest, Codeforces round 809, which I didn't do too well on if you watched my last video. But after the contest I was able to upsolve two more problems, and I just wanted to show you guys the solutions because I think the problems were really cool. And yeah, let's get started. So in the first question, basically you're given a string of n characters and also an integer m, and by default every single letter in that string is going to be set to the letter B, and your goal is to create a lexicographically small string as best you can. And basically what a lexicographical order is like the way dictionaries kind of sort the different words in the English alphabet. Basically the higher the letter, like let's say in this one C is the highest, then this one contains the most weight. So everything will be ordered based on their first letter, and then if they're the same then the second, and if they're the same then the third, and so forth until there's a letter that's different. And the letter with the least weight, which is like from A down to Z with the lowest to the highest weight, then you want that to be, that would be defined as lexicographically smallest. So let's say we have a letter A, B, and C, and basically what lexicographical order is it theoretically assigns each letter with like a weight, and this is 1 because it's the first letter in the English alphabet. This is 2 because it's the second, C, and so forth. And the smaller it is, it means it has like lower letters such as A in the front. So this would be smaller than let's say D and C. So that's basically what lexicographical order is. And this problem becomes immediately easier when you realize that what you have to do, which is if you're given oh yeah, I forgot to mention, uh, so every single index from 1 to n inclusive, you're allowed to perform either replace the AI letter with with A, or the m plus 1 minus AI letter with A. And basically you want to check if the AI letter, so if I is equal to 1, you want to check if this is higher in the position than, or a lower number than m plus 1 minus A sub I. So that would be 5 plus 1 is 6, minus 1 would be 5. And yeah, it's smaller. So basically you want to use the first move. You want to replace the AI letter with A instead of this. So you have a choice. Either do this or this. And you want to choose whichever one will affect the lowest number. Because again, lexicographical order means that you need to affect the one in the higher position. So if you're given like B, the default, a bunch of B's, you want to affect this one before anything else, such as this one, because this one carries the most weight and is most important to lexicographical order. And so I'll just show you the code because I guess it's pretty self-explanatory. You just check if the AI letter is lower than the m plus 1 minus AI. So I created a map, and then with key value pair of char and int, and then if the map doesn't have like this, and it doesn't have m plus 1 minus AI, and m plus 1 minus AI is less than AI, then you can add you can do the second move. I'll refer to m plus 1 minus AI as the second move. And otherwise you add 1 to the AI, and all this is doing is just checking if whether the AI is lower than the m plus 1 minus AI. And you can take a look at it or pause it, and yeah. I'll move on to the second question. So in this question, you're basically given blocks, or you're given a certain number of blocks, so 7 blocks in this first test case, and each block represents a different color. And so this would be, let's say, red, like 1 is assigned to red, 2 is assigned to blue, 3 is assigned to green, then this one would be red, blue, green, red, blue, green, etc. And basically what you have to do is you want to see like how high you can stack each color. So for example, for 1 you can stack it a total of 3 times, like the maximum is 3, because if they show it here, then it would be here, here, and here. But there are some caveats, such as you can't place a block directly under the previous block. But this doesn't matter too much when you realize like the pattern that you should follow, and that is, as long as the distance between the same colored blocks is even, then you're allowed to place like the same colored block between it. Because let me draw it out. For example, if we have let me denote it by like the starting character of the word. So R would equal to red, B would equal to blue. So in the first test case, you're given 1, 2, 3, and so in the first move we have to place the 1 down at 0, 0. It's just the rule. So we place it down at the bottom. Let me move it lower. Okay, and after that we're given 2, and where do we put it? Well, we don't want to put it directly on top of it because that would ruin the chain of it, and then it won't be maximum anymore. And so we can either put it here or here. I'm just gonna put it over here for like repetition's sake, and so over here will become blue. The next one is 3, and so now we do the same thing, but we put it up now because now we're 1 away, and the next one's going to be red, so we put it to the left of it, and therefore now we have a tower of 2, which is better than a tower of 1, and so now this is the new maximum. And let me display why an even number distance, and when I say distance, I mean, so this is red and this is red. The distance is between it, like right here. So if it's even, you can do a sort of loop. Like let's say we have 4 as a distance, a theoretical distance. We can put another one here, 1 above, 1 over here, and then place the red, because then that would be a distance of 4. And this is always optimal. Like we would always want a distance of an even distance to make a higher tower, because if we ever have an odd distance, like let's say 5, it would never work because we would have to put it here, and then let's say 1 here, 1 here, and then it won't work. And so, and notice how we can't place it diagonal. So it's not like we can do this as 5 like that. We can't do that. So we must place 1 here, here, but now it's unreachable. Now this is unreachable, and therefore it proves the point that an even number distance is always the best. And yeah, basically in the code you just want to check the maximum number of even distant numbers. And if and only if the numbers don't appear, then that element will be 0. So let's say in this case 1, 2, and 3 appear, and yes, 1, 2, and 3 are queried, but the rest of the numbers 4 through 7 inclusive, they're set to 0 because they're not defined at all. Because if they were defined at all, like at any point, then it would be a 1. And you can take a look at the code over here. Basically what I do is I set all the numbers to 0 in the array as default. So when I print it out later, it'll be set to 0 if it's not defined at all. And I input the elements, and basically I check if I have not visited before, like if I haven't visited before, or the distance between it is, or the current index is different from the last known location's index. So let me explain that further, because I kind of explained it confusingly. So to lower time complexity and not keep an entire array of like indices, basically, or like a adjacency list to check if the indices are different. Basically, what you can just do is create an array of just the previous known index. So for example, let's dry run the first test case. So we have 1, 2, 3, 1, 2, 3, 1. Let me write it down here. 2, 3, 1, 2, 3, 1. Basically, you check if it's not been visited before. So if 1 has not been visited before, which it hasn't because it's the first element, then you want to set this to I. So this is the current known index of 1. And so that would equal to 0. So A of 1 is 0. And the answer for 1 gets added on, because basically what the answer array keeps track of is the maximum height. And currently the maximum height is obviously 1 because there's one block that appeared and it's a height of 1. And so let me just keep track of the tallies. So this gets 1. And next we check the next element. Oh, sorry, I used 1 indexing because this is the part that tripped me up a little bit, because if you set it to 0, then that index gets set to 0 again. Like for example, if you set this to, if you use 0 indexing for the loop, like from 0 to n minus 1, then basically what it does is, if it hasn't been visited before, or if the parities of the index and the element are different, then A of C of I gets set to 0. And then that's not good because it'll become a positive feedback loop and keep repeating. But if you set it to 1, then it'll stop. And I might explain that a bit later, but let me go through this first. And so next, you get 2. 2 hasn't been seen before, so A sub 2 would equal to 2. So A sub 2, let me create a new one. A sub 2 would equal to 2. Because again, this is element 1, this is element 2, this is element 3, this is element 4, 5, so forth. And so this is 2 because you want to check like the index it's at in order to check the distance. And if you've seen it again, then basically what it does is, if you've seen it again and that index is different from the previous known index, for example, we bump into 2 again at index 5, and the index for this is 5, or the parity would be odd, while this one, where we last seen it, would be even. And since it's different, we know that the distance will be 2. So the distance is even if and only if the parities of both elements of equal elements are different. And so, yeah, so either it's not been here, like you haven't created yet, or the distances are different, then we know to add it to the previous known location, add the current element to the previous known location, and add 1 to the tower. And I hope you guys understand that. If not, I know it could get confusing. You can just comment down any questions and I'll answer it right away, or as soon as possible. And moving on to the last question. Ooh, this one was fun. So basically, you're given n number of towers and their heights. So it's kept in an array of n elements, and your goal is to create the maximum number of towers that are taller than their adjacent towers, but in a minimum number of moves. So let me explain that further. Okay. So in this case, in the first test case, this one, we have a tower of 2. I'll just represent them as blocks because it might be easier to understand at first. 2, 1, 2. So it's shown as numbers, but this is 2, 1, 2, 2, 1, 2. Basically, your goal is to create as many tall towers, and a tall tower is when it's larger than both its left and its right. Strictly greater than. So it can't be same height. It can't be like right here. It has to be like one above, at least one above. And you want to do that in a minimum number of turns. And in one turn, you can increase a tower's height by 1. So you can add 1. And yeah, so in this test case, originally it's like this. And in one move, you move it to here. So now the tally is 1. And in another move, since it's right now it's equal, and you want to make it taller, you have to add another 1. So now it's strictly greater than both sides. And so now it's 2. So the answer for this test case would be 2. So the pattern that you need to recognize in this problem is the fact that if the elements are odd, like if there's odd elements, or if n is odd, sorry, then you know you can only, or the most optimal way is to affect the non-edges. Oh, and I forgot to explain the edges, like 1 and 3 and 2 and 3 can't be affected because, or you can't make them tall because there's nothing to the left of 3 and there's nothing to the right of 2. So it's only the only towers that could theoretically be tall are the ones being sandwiched in a way. And so yeah, so if n is odd, then the most optimal way is to get the one besides the edge to be odd, and then after that in increments of 2. So let's say we have, I'm just representing them as circles at this point because it's easier to draw. So let me get 7 of them because I think 7 is big enough. So we choose the one on the edge. So if n is odd, like 7, so when n is equal to 7 in this case, we choose the one to the right of the edge, like this one. And then after that in increments of 2. So now this one, and then this one, and that's it. In this case, there would be 1, 2, 3 tall towers, and that's just the most optimal if n is odd. But now if n is even, so we add 1 more. That's a pretty ugly 8. So when we add 1 more, basically we want to check if okay, so now here it gets complicated. So if n is odd, we could do this. My original thought was we do this, and then the next one we check which one has the minimum number, either these 3, or all shifted to the right, like these, and these. But as you can see in this test case, these aren't necessarily pairs, but then they're the most optimal choice because this would still be a maximum tower of 2, and that's the largest you can possibly do. But then the answer would be 0 because these are already tall towers, so there's nothing you could do about it. And so the solution ends up being if n is even, then you have a choice. Basically what I do is I increment from this one, and I collect the elements from every increment of 2. So let's say this is 5, 1, and 3. Then this would be 9 total so far. And then I start again at this loop. And let's say this is 4. This one's 6. Sorry, that's pretty bad. Yeah, I can't erase that. It'll have to be that way. That one's 6. This one's 4 again. This one's 0. Oh, sorry, we don't even need that. So now we start at this one. We add 4 to it, so now it becomes 13. And then we subtract this one, so it becomes 8. And along the way, we want to find the minimum. So we keep checking if that's the minimum out of all of them. And I noticed this pattern because if you see, like, in order to maintain the maximum number of towers, you can only have a gap of at most 2, like this. So, oh yeah, it'll have a gap from here to here. So let's say the element 5 gets removed, then, and this doesn't exist because then right now we're solely checking the first one and we're going like this, but we haven't checked this yet. So if this is the minimum, then we just remove this and then this gets added, and so the gap can be at most 2. And for the code, fairly simple. You have to use a long for answer because it can get overflowed. But other than that, at first you check the heights. So you go from 1 to n minus 1. And then you check each height, like how much you have to add to that element in order to make it tall. So for example, if we're using the 1 2 1 example, or 2 1 2, let me erase this. Basically, in this case, it goes over element 1, and then it would just be this one, because this is the first element, because this is 0, this is element 1, and this is element 2. So it checks element 1. It says if, so check like the maximum number, and it has a 0 here, because if this is negative, then we don't want the height to be negative. It'll always be at least 0. And so we check if 0 is larger than h plus 1, or the maximum h plus 1 or h minus 1, because if one of them is the maximum, the rest are constants. So whichever one's larger in this one, either this or this, it'll still be the larger with this added on. And so basically it checks, and since both are the same, in this case 2 and 2 are the same, it could be either of them, so it'll be 2, and then subtracted by 1 plus 1 would be a total of 2, as I showed before, to make this stack up. And the way this small formula works is it takes the largest one, so either of them, because it could be arbitrary in this case because they're both the same, so 2, and then it subtracts it from this one to get the distance between here and here, and that's a distance of 1. And then after that, it adds 1 more, because you don't want it to be less than or equal to it. You want it to be greater than. And then so that would be a total of 2 added on. Because then this subtracted by this is 1, and then add another 1. So after you've gotten all the heights from n to n minus, from 1 to n minus 1 inclusive, next you want to check if it's odd. If n is odd, then that was the first case I was telling you guys about. The maximum possible tall towers would be to go to the edge, to the left edge, and then 1 more, and then increments of 2. And you can see that it starts at the 1 after the left edge, which would be index 1. Or, so if we have, let's use these again. Or no, let me just create new ones because those are kind of messy. So yeah, if we have odd number of towers, we just start at index. So let me write their indices. We start at index 1, and then we go skip 2, and so forth. And that's just the maximum. And you add to the heights, and then you output answer if it's odd. And otherwise, you create a count, and you start at index 2, and you go in increments of 2. So that was this example. Let me erase unnecessary stuff. And I guess I'll recreate the bubbles. So now if n is even, okay, then you start at index 2, which would be 0, 1, 2, 3, 4, 5. This one. You start at this one, you hop 2, add the elements from this one, and now that's your current counter, and now you got all you need so far, and then you set answer to count because that's going to be your largest possible answer. You want something less than that, but this is the largest it can go. And now you start at index 1, which is this one, and then you check, you add this to the total, and you subtract this. You add this and you subtract this. And you keep doing that pattern. So for this one, you add this and you subtract this. And along the way, you want to find the minimum. So every single time you do the add and subtract, you find the minimum. So currently, the maximum answer is like this plus this. And now you do the answer plus this and subtract this, and you check if that's lower than the previous answer. And if it is, that's the new answer. And now you skip 2, so you hop 2, and now you go over here, and you do the same thing. You add this, and you subtract this. Basically, that's going to counter cases such as this one, where it's not exactly a hop of 2 from here to here, but it goes 3. It goes 3 over to get to this one in order to create the most optimal amount of tall towers. Hopefully that makes sense. Yeah, and if not, again, you can ask questions. But yeah, that's basically what it does. Just checks if the gap can be. It just checks like the maximum gap it can be, because the maximum of tall towers is going to be. In this case, it's going to be 2, because it can't be this or this, and it can't be like next to each other, so it must be 2. But it could be either this 2, these 2, this and this, or this and this, and you don't know which one it is. And to check that, you basically check the maximum gap, and the maximum gap can be checked by adding one element and subtracting another in order to form the gap. And yeah, let me just show you that with that test case, and then I think this explanations video could be over. So if we have 1, 10, 1, 1, 10, 1. Basically, you discard these, or let me just include these instead of discard the ones we need to discard. So now it'll be these. So at first you add 1 to the total, and then you add 10, so now the total is 11. And so now answer would equal to 11. So that's a maximum answer so far. We want something smaller. And to get something smaller, we now check 10. We add 10. Okay, sorry, never mind. Those were the pure elements. We want the height. So that would be 0, 9, 10, 10, 0, 0. Yeah, my bad. And right now I'm just like finding the height and the height needed to get to be tall tower. So this needs this one needs to be 0 because it's already a tall tower. It's larger than both its adjacent towers, and this one needs 10 in order to be taller than this one. And so that's what I did. For this one, it'll be 10 and then 0. So then that would be a total of 10. And then later, over here, it adds 0. So 10 would still be 10, but it subtracts 10. So now the maximum is 0 because it subtracts this one, and it adds this one. This one's not included, and this one is. So that's basically how you find it. And again, let me emphasize that in order to form the maximum towers, the largest possible gap, like you can't have a gap larger than 2. I think there are multiple ways to check this. You can have like nested for loops, but this is the most efficient because it goes linearly. And yeah, so that's it for the explanations. I hope you guys learned something or understand some of the tasks now. And thank you for watching. I know it can be confusing, so if you have any questions, feel free to ask them. And if you enjoyed it, please like and subscribe because it'll help my channel. And thank you.